Welcome to the Module 5 Number Systems. So, before we begin Module 5, talk about something. So, in today's module, we'll be just going through binary number system and hexadecimal number system. It's just a very quick review of what a binary number system and hexadecimal number system is. The reason we have to go through is that because IPv4 addresses and IPv6 addresses uses these system, and we would have to do some conversions. So let's just go through some basic conversions between decimal, hexadecimal, and binary systems. And the reason why we need to study this at this point is because we just yesterday covered physical layer, where we talked about physical equipments required for creating a network or trying to communicate between computers. We need some physical components, and it included network interface cards, it included media, it included connectors, signaling, encoding, and so on. That only solves the physical connection between multiple computers, right? Now, those physical connections could be connected in any number of arrangements, okay? And then you will run into more problems once you physically connect these things, and that's when you start thinking about data link layer, which is above the physical link or the physical layer. And to discuss the data link layer, we have to first understand binary system, because in those layers above physical layer, as we start talking about data link layer and the frame header information, where we would have MAC addresses, and then on top of that, then we talked about network layer, layer 3, where we would have IP addresses. It's all going to be about binary, hexadecimal, and decimal system. So that's why we have to first go through this very quickly. It's a very small module. And then we will jump into module, this is module 5. Then we'll jump into module 6 and start with data link layer and see where you can go from there, okay? So we'll try to cover 2 modules today, because both are very small modules. So hang tight, okay? Module 5, let's talk about binary number system. Okay. So binary number systems consist of ones and zeros. So before we talk about binary systems, so I'm assuming nobody knows anything about binary system, okay? But everyone knows about decimal system. So what is a decimal system? Decimal system is decimal basically means 10. So you have 10 digits. So in your daily life, you're using decimal system in which we count up to 10, and then we start repeating those digits. So it starts from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So from 0 to 9, you have 10 digits, which we can repeatedly use to donate even bigger numbers, right? So that's why it's called decimal. So this is the base 10. When we say decimal system, that means we have a base of 10. So whenever we reach number 9, we run out of digits. What comes after 9? So if we have to mention something after 9, we have to repeat the previous numbers that we have used. Now, instead of 1, we can add 2. So like we can use 1 and 0. So then we say 10, which is a repetition of previous number, just we added another digit. And then it would be 11, 12. So after 9, we get into a repetition, right? So that's why it's a decimal system. Similarly, we have other systems as well. This is the only system that you are probably familiar with, but it's not the only one that we use. There are other systems that we can use as well. One of the other system is hexadecimal. Another one is a binary system. So let's look at the binary system. Binary is a base using base 2, meaning it has only 2 variations. So if in this case, if you are using a decimal system, you had 10 digits, so it spanned from 0 to 9. If I say instead of 10, you only can use 2 of them, and that's it, then what would they be? They would start from 0, 1, and that's it. You just use 2 digits. You used 2 numbers starting from 0, 0 and 1, and it's done. What would be the next number? Well, you have to repeat the previous number. So the next one should be what? should be 1 0, just like here. And the next one would be 1 1, and you're done again. Then you have to add another one here, and so on and so on, right? So you don't have any other numbers. You just have 0 and 1s, and you can also count with that as well. But it's not intuitive for us to think in binary system. Computer uses this system. Okay, so in binary number system, it consists only ones and zeros, and that's it. And these ones and zeros are called bits. This is a bit, this is a bit, that's it. Decimal number system consists of digital 0 through 9, which is this one that we saw. And that's why we call it decimal, because it's a base 10. So computer doing all the calculation, they only do that in this binary system. But for us, we don't understand binary system. So when we want to make any a sense of what's going on in computer, and when we see addresses and numbers, we want it to be first converted to decimal, and then we understand it. For example, we'll take examples later on. Okay. So similarly, all the addresses, even if we're using MAC addresses at layer 2 or IP addresses at layer 3, we have to first convert these binary numbers, because computers are using those addresses in binary system. But when we want to talk about it, when we want to type it, we want to type them in decimal system, because that makes more sense to us, not the binary numbers. So that's why we have to learn the conversion. How do we do the conversions between them? So normally, if we talk about IP addresses, the IPv4 addresses specifically, they have 32 bits, which are divided into 4 sections called octaves. Let me get this out of the way. Okay, they're called octaves. Inside each octet, we have 8 bits, which is 8 bits are also called 1 byte, separated by dot. Okay, so why do we do that? Well, for ease of use by people. So this dotted notation, it's also called dotted notation. It is converted to dotted decimal. So for example, if you have a computer here, PC1, it wants to send something to another computer here. Both of these computer 1 or computer A or computer B must have an address, an IPv4 address. So when it sends a packet, inside a packet, it will mention what is my address as a source address. And then who is he sending this message to? That will be mentioned in a destination address. And these addresses are IPv4 addresses if you're using IPv4. They could also be IPv6 if you're using IPv6, which is a newer version of the Internet Protocol. So in case of IPv4 only, we're talking about IPv4 here in this example. The IPv4 address is 32 bits long, meaning you would have 32 bits like these. 000010010, whatever the address is, it is 32 bits long. Now, if I tell you my computer address, if you want to ping something, go to command line. So if I want to ping a computer and its address is 32 bits long, imagine what I would have to type if I want to ping it. I would have to type 32 bits like this. Up to 32 bits. It would look something like this, and I would hit enter. Right now, it doesn't accept it because it is assuming the program is written assuming that I would give the address in decimal notation, not in a binary, right? So you can already see for us humans how hard that would have been if all the addresses were like this. In reality, they are like this. They are 32-bit long addresses. But when we try to type it or work with it or use it in tools like ping and traceRT, we have to first convert them into decimal. And computer always shows them in decimal notation to us. For example, if I do ipconfig just to check out what is IP address of my computer in this case, well, it tells me my IPv4 address is 192.168.18.80. Well, that is the decimal notation because now it's been converted from binary to decimal so that when I read it, I understand it easily. And even still, there's another problem. if this 32-bit address was converted as it is, it would create a big number, something in, because with 32 bits, you can represent up to 4 billion numbers, okay? So instead of converting it directly, it would have created something like 4,600,000,000 and something number, which would be again very inconvenient for us to remember or talk about it or type it. They also divided this 32 bits into 8 bits of groups. And these each group, so you become, so how many groups you would create if you divide 32 into 8 bits? You'd create 8 bits of 4 groups of 8 bits. And each of this group is called octet. Why is it called octet? Because oct means 8. We have 8 bits in each group. And then you put a dot in between all these groups. That's how you get 4 groups. And that's why when you look at my address, it is divided into 4 groups. Once you do that, then you convert these 8 bits only to the decimal. And then these 8 bits to the decimal, every group or every octet, you convert it to decimal separately. And that's how you get this IPv4 address, which looks like this. Okay. This is only for us so that we can work with them easily and do quick conversions. There's a video on that. Whatever we are studying right now, there's a video in the Netacad as well. You can go into your account and check that video as well. That also gives you the similar explanations. Okay. So now in decimal system, which you are more familiar with, think about this. How do you write bigger numbers with big values? Well, if you, for example, if you have a decimal number 1, 2, 3, 4, it is just 1 has just a value of 1, 2 has a value of 2, 3 has a value of 3, 4 has a value of 4. But putting them in a different position gives them much higher value. And we intuitively know by looking at this number that this is 1,234. But there's a mathematical way where we can come to a conclusion that why its value is 1,234. If you just remember your school days when you are learning maths, you would know that each number has a positional value. So this is called a positional notation in decimal system in this specific example. So the first number you see, it is called ones. The second number you see has a positional value of tens. The third number has a positional value of hundreds. And the fourth value has a positional value of thousands. And then you have 10,000 and then millions and so on. But how did those values came out? That's because of this position. Because we are using decimal notation, our base is 10. So the first position has a zeroth position. So first position, we normally in our conventional language, we call it the first position, but in computers, we call it the zeroth position. So the zeroth position value comes from the base to the power its position. So it's 10 power 0, 10 power 0 equals 1. Then the first position after the 0 is 10 power 1, which equals to 10. Then the third position, which is 2, it's 10 power 2, which comes to 100, and 10 power 3 is 1000. This is how we come up with these positional values, that the first position is ones, the second position is 10, third is hundreds, and this is 1000. And the actual value of the number that we want to find out, you just multiply these number with its positional value and then add them together. Like 1 in 1,000 is 1,000. 2 into 100 is 200. 3 into 10 is 30. And 4 into 1 is 4. And then you add all these numbers together. So 1,000 plus 200 plus 30 plus 4. And you get to this actual value, which is 1,234. It's no longer 1, 2, 3, 4. It is 1,234 when you multiply each number with its positional value and add them all up together. That's it. It's a very simple idea, and hope it is very clear. And this is very important that it is clear for you. This is intuitive. You understand it. If you understand this, you can understand binary system because it follows the exact same rule. Okay, so let's look at the example of binary now, how you could do the same thing in a binary. Okay, so the binary positional notation system is exactly the same, except the base in this case is 2 because it's binary. It's no longer decimal, right? So binary has a base of 2. So the first position, please explain once more. Okay. Let me. Well, I think if I explained, well, let me do it like this. So I don't know what extra to explain in this case because it is so simple. If you just recall that you have learned this in your normal maths at school or college level, at school even, any number that you have in decimal system, it's each number has its value. Okay, so if you have a number 1 2 3 4 and you want to find out like what is the value of each number in this 1 2 3 4, so you can already see that the number 4 does not hold as much value as the number 1 holds it, because this 1 is 1000 actually, and the 4 is just a 4 alone. Okay, that's what it means. And the reason you intuitively know this is because you work with decimal numbers in your general life. So you understand, like, whenever 1 is on the left side, it has a greater value than the number that is on the right side. This is just the same thing explained in mathematics. Okay. So the first position has a value of 1. So you just multiply 4 with a 1, it is 4. The second position has a value of 10. So you multiply it with 10. So 3 multiplied by 10 is 30. The third position has a value of hundreds. You multiply it with 100, so its value is 200. And this one position is actually 1000, so you multiply it with 1000, it becomes 1000. And then you add them all up. 1000 plus 200 plus 30 plus 4. And that's how you say the actual value of this number is 1234. Okay. Similarly, in binary system, instead of 10, you are using base of 10. So anything in binary, the first positional value of the binary is 2 power 0 equals to 1. Just like you had a 10 power 0 equal to 1 here. Similarly, you have 2 power 0 equal to 1 here. The second position is 2 power 1, which equals to 2. So the second positional value is 2. Over here, your second positional value was 10 power 1 equals 10. So the positional value in your case in decimal was 1, 10, 100, 1000, 10,000, and million, and so on. Similarly, if you calculate it in binary, you get this series 1, 2, 4, 8, 16, 32, 64, 128. And we only count up to position number 7. Why? Why are we only counting up to position number 7? Because this is the only positions that you need to memorize or understand in order to do conversions for IPv4 from binary to decimal and decimal to binary, because in IPv4 addresses, we have octets which has 8 bits. And this is exactly 8 bits. From 0 to 7, you can do now conversions for 8 bits if you just remember this series, which everyone should memorize. 1, 2, 4, 8, 16, 32, 64, 128. If you just memorize this, everything will start making sense. Okay. So now, if you have a value, if you have a number in a binary system, you can very easily convert it into a decimal system if you just remember this. So for example, here's an example of a binary number, which is 8-bit binary number, meaning it is just one part of this IPv4 address. It is an octet. Okay. So if you just want to convert an octet, which is in a binary, to a decimal, what do? You just put them in a proper positional value. So these are, so you can, on top of these numbers, you just type or memorize these, that this is this first 0, its value is 1. The second is 2, and 4, 8, 16, 32, 64, 128. And you write down this number just below its own position. So it is 1 and then 6 zeros. So 1, 1, and 6 zeros. Now, to convert it to decimal, just multiply each number with its positional value. So 1 multiplied by 128, 1 multiplied by its position is 64, and then all other zeros are multiplied with zeros. All the positional values are multiplied with zeros. Now, just add them up together. So 1 multiplied by 128 is 128, and 64, everything else is 0. And if you add 128 and 64, you get 192. What is this 192? It is the conversion. So this is the binary number, and this is the decimal conversion of it. Okay? So this binary number is written as this in decimal. So if you convert 192 back to binary, you will get this, which is right here in my address, 192. So this 192 is actually 11 and then 6 zeros in binary, which is the actual binary address of my computer, starting from 192. Obviously, this is just one octet. You have to do it 4 times to get the full IPv4 address. Okay. So this is an example of a full IPv4 address. So if this is a full IPv4 address and it has dots here after each 8 bits, you have 4 groups or 4 octets. And if you want to convert it, what is the equivalent of this IPv4 address in decimal? What is the IPv4 address in decimal? Well, again, you just write these values 1, 2, 4, 8, 16, 32, 64, and do this conversion for each octet. So this is the first octet, 1100. So it is very easy to do calculation. Wherever you have 1, you only have to count those. You don't count the zeros at all, because 0 multiplied by anything is 0, and if you add them together, it doesn't amount to anything. So straight away, forget about zeros. Just focus on 1. And 1 multiplied by its value is always the same value, so you don't even have to focus on the ones. You have to just focus on the values where you have 1. You only have 1 for 128 and 64. So just add 128 and 64 together in your head, and you quickly convert it into decimal, and that's it. So eventually, it comes down to 128 plus 64, and that is your decimal equivalent of the first octet here. So this is 192. For the second octet, again, you just put the values. You have 1 zeros, so just forget about the zeros. Don't even think about the zeros. And wherever you have 1, look at the value 128, 32 plus 8. So you're just adding 128 plus 32 plus 8, which amounts to 168. For the third one, again, forget about the zeros. Don't even think about the zeros. Only think about the ones. You have a 1 for 8 position, 1 for the 2, and 1 for the 1. So 8 plus 2 plus 1, you get 11. Last one. Again, don't even think about the zeros. Forget the zeros. Just focus on the ones. What is the value of 1 here? 8 plus 2 is 10. So the decimal IPv4 address is 192.168.11.10. Okay? It's very simple. If you don't understand it, it's fine, because we have other modules coming up where we will be doing it again. But at least you should get the high-level idea of how do we do conversion between decimal and binary, and also how an IPv4 address looks like. There are 4 octets. In each octet, we have 8 bits, and we do conversions between octets only in 8 bits, not the whole 32-bit address. Okay. How would you do the reverse process? I mean, in this case, you had a binary address. You converted it into decimal by just adding the values on the top of where you have 1. The reverse process actually also starts from the same thing. Again, as I said, if you remember this series, which is the positional value of a binary system, then you can do all sorts of conversions. So again, anytime you have to do conversion, either from binary to decimal or decimal to binary, just think about this series, and you will start doing it automatically. So for example, here we have, do we have a number to convert? Start, where is Okay, this is just an algorithm to show you how, if you have any number, how would you go about. Whenever you have a number, let's say I give you 200, you have to start from here. Look at the first value. Is 128 greater than the number you are trying to convert? Okay, is the decimal number of the octet, like this, is it equal to or greater than 128? So that's the question. The number that you have, for example, it's 200. Is it equal to or greater than 128? If it's not, then you add 0 here. Okay. If the number you're trying to convert is actually greater or equal to 128. So in our case, we have a 200, which is true. It is greater than 128. Then you add 1. You would add 1, and then you subtract 128 from that number, and whatever is remaining, you start doing the same process against that number again. It's easier if you go through an example. Let's see. So for example, you have a number 168 that you want to convert to binary. So we will apply the algorithm that we just saw. The algorithm says, is 168 greater than or equal to 128? If it is a yes, which it is a yes, then we put 1 in here, in this position. And then we subtract 128 from this number. So 168 minus 128, it's 40. And we start the same process for the 40 again, but for the second position now. Is 40 greater or equal than 64? If it's a no, then you put a 0 here and move on. Next is 32. Is 40 greater than or equal to 32? Which is a yes. If it's a yes, simply put a 1 here and then subtract 32 from 40, which gives you 8. And start the same process for the next position for number 8. Is 8 greater than or equal to 16? No. If it's a no, just simply put a 0 here. We did this for 16. Now let's do it for 8. Is 8 greater or equal than 8? It is an equal. Then put a 1 and subtract 8 from 8. You get a 0. Once you reach 0, it's over. So you put all zeros in here. It's done. So this is how you converted a decimal 168 to a binary number. Now, obviously, this is a bit confusing. You'd have to go through it again and again, and you'd have to do some practice to learn it properly. Eventually, you have to learn it enough where you can do these steps in your head. For most of the time, at least for the exam purpose, you should be able to do this in your head. If you can't do it in your head, it is still okay, but that should be your goal, that you could do it in your head. If you can't do it in your head, it is still okay, because in the exam you will have access. You wouldn't have access to a calculator, but you would have access to a small whiteboard with a marker where you can quickly just type these values 1, 2, 4, 8, 16, 32, 64 and go through this process manually if you would. But once you go through it a few times, it's very intuitive that you don't need to go through this process. You could just do it in your head. Okay. This was a quick conversion. So routers and computers understand only binary, and that's why humans work, but humans work in decimal. So it's important for you to gain a thorough understanding of these two numbering systems and how they're using networking. So this is, again, I showed you my computer's IPv4 address. It looks like this: 192.168.10.10. Each number that you see is actually a representation of 8 bits. You would have to convert it into its own 8 bits. This one is own 8 bits, and this one has its own bits. So this would be the actual binary number or binary address of your computer. What you see as 192.168.10.10, that is a conversion of the binary IPv4 address that you have for you, so that we can read and quickly understand. Because if I just share this number with you, it doesn't make sense with you. You can't even tell. If I give you two addresses like this, it is even hard to tell for you whether they are same addresses or different, right? Similarly, we also have to understand how do we conversion between hexadecimal number system as well. Well, first of all, what is a hexadecimal? Just like we did a binary, so in a decimal you have 10 numbers from 0 to 10. And if you keep counting from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and you run out of numbers, then you start repeating again with 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, right? And you keep going. Similarly, with the binary number, you just have 0 and 1. And what would be the next number? Well, you repeat it again with 1, 0, then 1, 1, and you run out of numbers again. So you add another 1 here, and you start from 1, 0, 0, 1, 0, 1, 1, 1, 0. When you reach triple 1, again, you have to add another 1 and start from zeros again and keep going until you reach quad ones. And if you want to keep counting, you will have to add one another again here and start from quad zeros and keep going, right? In hexadecimal, hexa just means 16. There's a base 16 in this case. If you start from 0, 1, 2, 3, 4, 5, 6, 8, 9, and you still have more symbols. So remember, these 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 are just symbols. In decimal, we just have 10 symbols from 0 to 9. But in hexa, we have 16 symbols, and these symbols start from 0 and goes up to F. So after 9, we have A, B, C, D, E, F. And after F, we say we ran out of symbols or numbers. Now we have to start repeating. Okay? So this is 9, and A is not 10. 10 is for decimal system. This is A. Okay? So 0 up to F. And what would happen if you want to count more in hexadecimal system after F? Well, just like the other system, you would start with 1, you would add 1 more here, and start from 0 again. And it will be like this. Now, it looks like it is a 10, but its actual value is not 10. Its actual value is 16. It just looks like 10 because this is hexadecimal. So the 10 in hexadecimal does not have a value of 10. It has a value of 16 if you convert it to decimal. Okay? Why are we studying hexadecimal? Because IPv6 addresses uses hexadecimal notation. Because IPv6 is a 128-bit address, even such a long address, if you write it in a decimal system, it still doesn't make any sense. It's just very big number. So that's why we start using hexadecimal notation so that it looks smaller. Even in hexadecimal notation, it still looks very long, but that's the best we can do. So for IPv6 address, every 4-bit is represented by a single hexadecimal digit. Every 4 bits in binary is represented by one single hexadecimal number. Why? Because with 4 bits, you get 2 power 4 equals 16 unique numbers. Okay? So with 4 bits, you can represent one hexadecimal number. That makes IPv6 address a total of 32 hexadecimal address. So you have 4 hexadecimals here, 4 hexadecimal here, 4, 4 here, and each hexadecimal is again denoted by a 4-bit number. Okay. There's a video again on a Netacad in your account that explains these things again in a video. You should go and watch that. Now the question is, how do we do conversions for hexadecimal? Do we have to learn more things? The quick answer is no. Once you've learned the decimal to binary conversion and binary to decimal conversion, the hexadecimal conversion also uses the same system. You just have to go through 2 steps. So for example, if you have 168 and you want to convert it into a hex using a 3-step process. So if you have a decimal number like 168 in a decimal, this is a decimal number, okay? So if somebody gives you a number and wants you to do a conversion, it is important for you, for them to also tell you what base or what system this number belongs to, because 168 could also be a hexadecimal number as well. You wouldn't know if I don't tell you. So you must ask whoever is asking you a question. He must somehow tell you which system this number belongs to. Is it a decimal number or is it a hexadecimal number? In this question, we have been told that this is a decimal, okay? And we want to convert it to hex. So the process is easy. First, you have to convert 168 to a binary number. Now, can anyone tell me how can I quickly check whether 168 is actually this number in binary? I can do mental calculation in my head very quickly. Whenever I see a binary number, I start thinking about this, like this 0. I just start typing tiny positional values on top of them. 1, 2, 4, 8, 16, 32, 64, and last one is 128. And then wherever on which value I have a 1, I just have to add those values. So it's 128 plus 32 plus 8. So 128 plus 32 plus 8 becomes 168. Okay? That's how I know exactly how to convert these things in my head. Okay? So now you have the binary number, and then converting binary to hex is very easy if you just look at this table. It already gives you that hexadecimal 0 in binary is 4 zeros. A 1 in binary, a hexadecimal 1 in a binary is 0001. A 2 is 0010. A 3 is 0011. Again, you don't have to memorize this if you're thinking that you have to memorize this. This is also done through the same values system. If you just imagine that the first position is 1, the second position is 2, the third position is 4, this fourth position is 8. So 1, 2, 4, 8. So let's say if I want to see how would number 9 look like, I just have to look at these numbers. 8 plus 1 would be 9. So first position should be 1, and the last position should be 1, and the middle 2 should be 0. So that would make it 8 plus 1, 9. And if you look at it, it is exactly like that. So let's say I have to calculate for 1a. How would be a represented in a binary system? Again, I just have to think of these numbers. Well, a is basically equal to value 10 in decimal. How do you convert 10 into binary? Well, look at this. If I do 8 plus 2, that would be 10, which means 8, and this should be 0, the 2 should be 1, and last one should be 0. So 8 plus 2 would be 10, so it would be 1010. And if you look at it, oh, it is 1010. If I want to convert f into binary, you should just memorize this. Very easy, because f is, if this is equal to 10, this is 11, this is 12, this is 13, this is 14, and this is 15. How do you type 15 in a binary? Well, if you do all of them together, 15 is the maximum number in 4 bits. So 8 plus 4 plus 2 plus 1 becomes 15. You can't do anything else, which means everything should be 1, 1, 1. That's why this is the final value in binary. So this is something you either memorize, or either you should be able to do it mentally very quickly, because this is a very small number. So back to this question. 168 first converted into binary, and once it's converted into binary, just add it into a group of 4s, convert it into group of 4s. So look at this this 4 numbers, and then look at these 4 numbers. We just talked about this number. 1010 was equal to 10, which in hexadecimal is actually a. And this 1000, well, it is very easy. What is the position of this? It is 8. Everything else is 0, so it should be 8. So 168 in hexadecimal should be A8. This is how to do a conversion. So you first convert decimal to binary, and then convert binary into a hexadecimal. Okay, this is a second example. Again, same thing. I'll leave it for you to go through it, because the solution is already provided here. So in this case, it's a backwards. So you have a hexadecimal number D2. You want to convert it into decimal. Again, very easy. You convert D separately to a binary and 2 separately to a binary. Okay, so the D when you convert it into binary is this, and 2 when you convert it into binary is this. You can simply think about 1, 2, 4, 8 above them, and you can confirm that this is actually 2. You can do this one as well, 1, 2, 4, 8. And you can simply confirm this is like 8 plus 4 plus 1. So it will be 8, 9, 10, 11, 12, and 13. 13 is D in hexadecimal because A is 10, B is 11, C is 12, and D is 13. This is how you confirm. Okay, this is good. So if this is right, we can just combine these two binary numbers like this now. And now again, think about these numbers: 1, 2, 4, 8, 16, 32, 64, and 128. And I can already start counting. Well, it has 128 plus, again, it has 32. Then 16 is 0, so we don't count it. And then we have 8, so plus 8. Then then we have 2 is 1, so 2. So if you add this all together, you get 210. So D2 is equal to 210. Okay. So you can go to your module in Netacad. So there is small questions for you and quizzes that you can go through, so you can practice them and learn and see how much you can do. And that's how you do your practice. There are no packet tracer for this. This is just very quick introduction to binary, hexadecimal, and decimal system. We will take a small break and they'll come back within 10 minutes and start a new module, because this is a very quick introduction. If you don't understand something, don't worry, go through your Netacad account. There are videos over there as well. And if you still don't understand, you can throw me a question in the group as well. Plus, we would also be doing this thing again and again. This is the base of subnetting. Somebody is asking, yes, submasking. I don't know what is submasking, but yeah, this is a base for subnetting, if that is your question. You have to understand this, and then after this, we will be in other modules, different modules, we will be starting to understand what actually subnetting is. Okay, so I'll see you back in 10 minutes. Okay, thank you, Jared. So Jared can see it, so let's begin. Okay, so the purpose of data link layer is to provide communication between network interface cards. Network interface card on these computers, which is provided by physical layer. Physical layer solved the physical connectivity problem. So because physical layer solved that, it designed a network interface card, a connector standard, and a cable, Ethernet cable, or a wireless medium, antennas, whatever you needed. And finally, these computers are connected together physically somehow, maybe through wireless connection, using Wi-Fi, or maybe through Ethernet cable or fiber optic, whatever you chose based on the trade-off that we saw yesterday. That some are expensive, other have higher bandwidth, some can go longer distance, some are for short distance, and so on. So whichever you chose, you give the physical connectivity using those solutions that you had, which were defined by a physical layer. Now you have to send a frame or a message from this computer to this computer using that physical connection that you have. And above the physical layer, you have this data link layer, which is responsible for sending that message using this physical connectivity that you have from here to here. Okay, so now there must be something in this message that can identify this computer and this computer at the data link layer. That is one responsibility of the data link layer. Okay. Another responsibility is that it should allow upper layer protocol to access the physical layer media and encapsulates a layer 3 packet into a layer 2 frame. So here is a physical layer, a layer 1. Here is the data link layer, a layer 2. And here's a layer 3 above it, and so forth, layer 4, 5, 6, 7. I'm not drawing it here. This sentence is saying that this is the data link layer, that it is the responsibility of a data link layer protocol to allow the upper layers, which are this one, upper layers, to access the physical layer, meaning that for all, whatever upper layers, layer 7, layer 6, layer 5, layer 4, layer 3 created, layer 2 has to provide a support for all these above layers so that it can be sent eventually on the physical layer 1. That is the purpose of layer 2. It is connecting the software world to the hardware world. You have hardware here at layer 1, and above layer 2 you have a software. So this layer 2, which is a data link layer, it has a very unique purpose, a unique function, where it has to provide a support for all the software above layer 2 to be able to use the hardware below it so that the actual data can be sent on the actual physical interfaces and physical media. It's a very unique function that the layer 2 is playing, okay? So that's why layer 2 has to convert everything by encoding it into a frame, which will look like this. And it also have to do some error detection and rejects corrupt frames. So it has to add these, all of these things, and we are going through them one by one. How does it support this and how does it solve this problem, okay? Again, in the same diagram, think about it. This is layer 3 network layer. This is layer 2 data link layer, and this is layer 1 physical layer. So if you look at the data link layer, because its responsibility is to allow all the upper layer, which are all software, to use the hardware, which is a physical layer. So that's why this layer 2 is divided into some sort of 2 sublayers. Okay, one of the sublayer is called LLC sublayer, another is called MAC sublayer. The LLC sublayer has a job to work with software, the upper layers, and the MAC sublayer has a job to connect with the physical layer. So it has some properties of the physical layer and some properties of the software layers, because it sits in the middle where it connects software with the hardware. Okay, now the MAC sublayer is the one we will focus more on, and this is also a reason that you can see that when TCP/IP Stack wrote software, they consider layer 2 and layer 1 as a single layer for this very particular reason, because you cannot 100% cleanly separate layer 1 from layer 2. They are really very closely related. In what sense? In this sense, for example, if at physical layer you decided to use, let's say, the copper cables, okay? You decided to use copper cables. Remember, from physical layer, we have multiple options to use at physical layer, right? So if we decided to use a copper cable with UTP or shielded twisted pair cable, which is one standard that the physical layer defined for us, and if we think that's a cheaper version that works for my solution, and I buy them, then I also must have network interfaces card where RJ45 could be plugged in on all computers, right? And once I do that, then on the data link layer, I would be using this Ethernet IEEE 802.3 standard for a software to encapsulate a frame which goes with this physical media. If I choose to use Wi-Fi at physical layer, then things would change a bit. If I use Wi-Fi, then I'm not using copper cable, then I wouldn't also be using the network interface card with RJ45 ports. I will need a different network interface card at a physical layer which supports Wi-Fi antennas, right? So if I select that physical media for my computer network to communicate, then at data link layer, specifically at MAC sublayer, my frame would completely, I will be using a different standard. My frame will look completely different than the Ethernet frame. Now I'll be using a WLAN frame, which is following 802.11 standard. And there is difference between those frames. Your wireless LAN frame is different than your wired frame, because wireless LAN has different problems at physical layer that needs to be solved, and wired LAN has different problems that needs to be solved. So every time you're changing the physical layer standards, you're also needing a specific solution at max sublayer as well that goes with that kind of hardware that you're selecting. Okay. Similarly, if you are using Bluetooth, RFID for, then you would be using IEEE 802.15 protocol at max sublayer. So the gist or the thing that you need to understand is that at data link layer, we have a max sublayer where we have multiple protocols that support different physical standards. So if you're using Ethernet standard using copper cables, you need Ethernet frame. So the data link layer would create Ethernet frame if you are choosing those type of physical standards. If at physical layer you're selecting wireless media to communicate, specifically Wi-Fi, then the max sublayer would be using 802.11 standard frame, which would have different values in its header when it creates a frame. Similarly, if you're using Bluetooth, RFID, or any other physical standard, different standard, you need a data link layer. At max sublayer, you need a different protocol standard to create that kind of frame. So this is what you need to learn or take away from this slide. And then there is the LLC sublayer, which remains constant, which takes or sends data or encapsulate or decapsulate from whatever it's coming from network layer. Okay, so this only deals with network sublayer. There's nothing much different here. Everything is different at max sublayer. And why is it different? Why do we have so many different standards at make layer? Why so many protocols? Because you have so many options at physical layer. So these options keep changing based on which physical layer component you are using, which standard you're following. Do you need copper cable? Do you need fiber optic? Do you need wireless LAN? Do you need Bluetooth? What physical media do you need to create your network? I hope this is clear. Okay. Now that you understand that, let's see what access to media means. Okay. So the do we talk about access before here? No. Okay. So packet exchange between nodes may experience numerous data link layers and media transitions. What does this mean? That whenever you are exchanging packet, let me in fact create something here. Okay. So if you have a computer here, this computer could be connected using a copper cable with a switch. Let's say this is connected to a switch, so this is a switch. And this switch could have, let's say, an access point connected with antennas, and that is connecting your mobile phone, your smartphone, with a Wi-Fi. So you have a Wi-Fi connectivity here, but there is a, let's say this is a UTP cable, unshielded twisted pair. So your computer is connected with a cable, but your mobile phone is connected with a Wi-Fi, and you can generate a message over here on this computer and send it all the way to this computer, your mobile phone, or vice versa. So this sentence, if you try to understand, is saying that the packet is exchanged between nodes may experience numerous data link layers and media transitions. It means that your packet, when it is traveling from its one source to destination, it is changing different, it is transitioning through different media. Sometimes it's going through copper cable using UTP. Maybe it's UTP here as well. But after here, it is using Wi-Fi, and eventually it reaches its destination. So when your packet, when it's transmitted from one source to a destination, it does not go through the exact same physical media. It transitions from different media, from one media to another media. Sometimes it's going through a copper cable, sometimes it's going through fiber optic cable, sometimes it's going through WiMAX technology, point-to-point wireless connectivity, or sometimes it's going through Wi-Fi. Whatever is coming through the path, it has to go through that path and eventually reach its destination. So there is a lot of variation coming in the path of a life of a packet when it goes from a source to a destination. If it is if it is changing, if it's changing the physical media, what else is changing? we just talked about, if you change a physical media, that also means that at the MAC sublayer, you're also changing protocols, because each media is supported by its own data link or sub MAC layer protocol. So when you are using UDP, you are using the Ethernet frame, right? It has its own standards. But when you wanted to send it over Wi-Fi, when the packet had to go through Wi-Fi, it was using WLAN Ethernet, which has its own format and its own protocol and own sources. Why is that? Why are we changing the data link layer protocol with each media? Because physical media has its own set of problems. The Wi-Fi media or the wireless media has its own set of problems. To solve these problems at data link layer, you have to use different protocols. Okay, we will get into those problems very soon. So at each hop along the path, a router performs 4 basic layer 2 functions. So for this packet to go from, this is called a hop. Any device between a connection is called a hop. So this is one hop, this is another hop, and this is another hop. So every time this packet has to go through a hop, it has to do these functions. A router specifically will perform basic layer 2 functions. So it accepts a frame. So in order to clearly explain it, let's now create the same example, but with the router. You have router 1 here connected to router 2, and that could be connected to a switch, and then a switch is connected to a computer. Over here you have another switch, or let's say it's a Wi-Fi here, access point, and then you have a laptop here that is connected to this Wi-Fi through wireless signal. And you want to send a message from here all the way to here. So every time it goes through a hop, so this message has to go from here to here. This is one hop, this is another hop, this would be another hop. So every time it changes a hop or goes through a hop, the router accepts a frame from the network medium. So this router is accepting a frame. So this computer will generate a frame. Remember, the frame is the actual thing that you are always sending on the physical line. Screen is stuck, only R1 is showing. Can other people see full screen? Can anyone else? Okay, it's clear now. Okay, other people can see it. It's probably your issue. All right. So every time a router accepts, it accepts a frame because we sent a frame. We always send a frame. It will have to de-encapsulate the frame to expose the encapsulated packet. So whenever a frame is received on a router, it will have to de-encapsulate. Remember now, what is de-encapsulation? When you receive a frame, it is a layer 2 information. On top of it, it has a layer 3 information. So every time a router receives it, it will read this information and then de-encapsulates it. It removes this entire frame header to expose what is inside layer 3 so that it can read the source and destination IP addresses. Okay, so it will de-encapsulate the frame to expose the encapsulated packet, read the information, and then it has to re-encapsulate the packet into a new frame again. Now this router, in order to send it out to the other router, it has to create another frame in which it will have the same layer 3 information that it saw, but it will create a brand new frame, layer 2, with new information. This is important, okay? We'll see why. And then forward the new frame to the medium of the next network segment. Why it has to do that? Because when it received a frame on this and it had to send it on this location, it is possible that this medium is different than this one. It is possible that this is UTP cable, and this one between R1 and R2 is fiber cable, following different standards. And in this one is basically, it could have been a Wi-Fi as well with this router. So it would be a WLAN. So every time a router receives a frame, it has to remove the frame information and then create a new frame when it's sending on the other side. Why it has to do that? Because the other connection to the other device might not be the exact same physical media. It could be a different media now. Okay? So that's one reason. Yes, Peter. So layer 2 basically sender information change, not just sender information, the source information also changes, Peter. Okay, we will get to that. So IEEE is also governed by these organizations, IEEE, ITU, ISO, and ANSI. If you remember, these are all those organizations which were also governing the standards of physical media. Again, think about it. Why same organization are responsible for physical layer are also responsible for data link layer standards? Because physical layer and data link layer, specifically the sub layer, which is what we call a MAC layer, are closely related. If you change something at the physical media standard, you have to change the protocol at data link layer for that media as well. Okay, so that's why it has to be responsibility of the same organization. If you change physical standard, you have to change the data link layer standards as well to accommodate those changes. Now that you understand up to this point, let's talk about physical and logical topology, okay, which we have talked about it before as well in physical diagram and logical diagram. So the physical topology shows the physical connections and how devices are interconnected. The logical topology will identify the virtual connections between devices using device interface and IP addresses scheme. We have covered these, I think, in very first module, the difference between a physical topology and logical topology. So there are different physical WAN topology possible. So when we are talking about WAN, think about long distance communication. So if you have a router in one city in one telephone exchange or internet exchange, and this is in city, this is city A, this is city B, there could be fiber optic cable going through under sea or underground. We have dug through that, and then this fiber optic cable eventually reaches up to the router and they get connected. In this case, we call this topology a point-to-point topology. So they're physically point-to-point connected directly with each other on this fiber optic. There is nothing else. If you send something from here, a message, it always is sent towards this router B. It cannot go anywhere else. There is no path, because on this link, on both ends, there are just these two devices. Nothing else is there. So that's a very easy one. Then there is a hub and spoke as well. So for example, if I connect this router to something, another router, and this router to another, usually a headquarter looks like this. If this is a headquarter exchange or a banking sector, so this headquarter is connected to all branches, and then it is called hub and spoke. So the center device becomes hub, and all the branches are called spoke. So this is another topology, a physical topology, where you connect these devices like this. And then last one is mesh, where you would connect everything together, every device connecting to every other device, which is very expensive because you have to use n into n minus 1 divided by 2 links. We're not going into those details, but these are some of the topologies physically possible when you are connecting device in WAN topology. You either just connect two devices together, in which case it's just called point-to-point, or you can connect all devices in hub and spoke fashion, or connect all devices to each other, in which case you just call it a mesh topology. The simplest one is point-to-point physical connectivity between two nodes or two routers. So it's called a point-to-point topology. In this case, nothing else shares these links other than these two devices. And everything that you send from here is always received on this one. This is the simplest point-to-point topology. And you can already see that at data link layer, a protocol written or a frame information written for this, it should be very simple. Why? Because there are hardly any problem to solve. It's very simple. You send something from here, it is always received here. There is no problem in this case. So the protocol for point-to-point WAN protocol is very simple and easy. The problems would arise, but the problem with this is that this is not usually what we have to deal with. We have other situations where more problems arises. If we just had to use point to point everywhere, then we wouldn't have any problem. The problem are with other topologies when you do other types of connection, like this. In your local area network, usually you have more problems, because in local area network you have a lot of computers that needs to communicate together. So you have a lot of different options. For example, you can connect all these computers using a star topology, where you have a centralized device here, like a switch or a hub, and you connect all computers to that switch or a hub, and now all of these computers can talk to each other. Now you have more problems. I hope you can see like why you have now more problems compared to this topology, where you just have two devices connected directly together. In this case, you have more problems. If this computer sends a packet on this link, how do you decide who gets this packet? Now, this is a new problem that you did not have in this case. So who is going to solve this problem? Data link layer has to solve this problem. How is data link layer going to solve this problem? By adding some information into the frame header through which we can identify who are you sending this information to. Are you sending it to computer A? Are you sending it to computer B, C, or D? That's how we would solve a problem. It's just an example, right? You are facing some problems because you connected them all together. Now the data link layer has to solve this problem. And then you could have these stars connected to each other as well, which gives you an extended star topology. There was another topology called a bus topology in old days, where you would, if you need a lot of computers to be connected together, this is another way. And this was usually a coaxial cable that we saw, which you use in TVs. And you connect each computer to that cable. So this cable they started calling this cable like a bus. This is a bus where data can transfer. And every computer that wants to communicate with other computer, let's just connect them together to the bus. So if you connect everything to this cable, this is a bus topology. Now all of them can communicate together, but this adds more problem. Again, it also has the same problem. If this computer sends a packet, who is going to receive it? That's a problem. How do we solve it? Again, data link layer has to solve this problem. Okay, we're not talking about how it's solving right now. We're just looking at problems, that there are problems, somebody has to solve it. Someone else said like, hey, like same thing like bus, but the whole cable is connected back together in a loop. So in this case, you have a same bus cable, but it's coming back and connected together, and all devices who want to communicate, they can just get a connection from here. It also has the same problem and a bunch of other problems as well. One of these problems is called access, media access. So the media access problem is, let's talk about media access after a while. Let's talk about some terminologies that you need to be familiar with to understand why are there so many problems when we physically connect. So physical layer has done its thing. It has created standards and everyone can connect together physically, but still, just to send a single message, we have other problems to solve. So to understand those problems, let's understand some terminologies. Half duplex communication. In order for two computers to communicate, there are two methods where they can do it. One is like a walkie-talkie problem, where you have two walkie-talkies. If you remember, you might have seen it. They're using a single frequency. If person A is communicating with person B on a walkie-talkie, if person A is talking, B must remain silent, and then B would receive it. Once A is done with its communication, it says over, then A stops talking, and then B starts transmitting. Why? Because they have a single frequency both are using. At a single time, only one person can send communication on that. The other side must receive or listen only. If they both start talking together at exact same time, this is what we call a collision. That these messages collide together, and then nobody can understand what has been talking about. Tree topology, I mean, it is same as the extended star topology. You can just rearrange it and it would look like a tree. It is all the same thing. Okay, we don't have to get into the details of that at a CCNA level because these are all obsolete. We're not using it. As we would see that in the next module, we'll start talking about that, hey, whatever you studied here, this is just for historic reasons so that you understand how networks evolved. We don't use them anymore. It's done. We have solved these problems, okay? So half duplex communication is like this walkie-talkie. You can only talk or listen. You can only transmit or receive. If two of the computer or more than one computer, any number of computers, starts talking or transmitting exactly at the same time, what happens? Collisions happen. Collision means that whatever you're using transmitting, whether it's electromagnetic signal or pulses of light or electrical signals that you're sending through the copper cable, if two signals, what are signals? They're just voltage levels in the copper cable. If you have a voltage level coming in this cable, if you have a cable and there are two computers connected to it, if you have a voltage level coming from here at the same time and a voltage level coming from here at the same time, they will collide each other. They will either have a destructive collision or constructive, whatever it is, but the original message will be lost. So on a single link, only one computer is allowed to transmit, other will only listen. When you are finished, the other computer can start transmitting and then you can listen. This is called half duplex communication, okay? So this is one way to communicate. Then another one is called full duplex communication, in which both computers can talk to each other at the same time. At the same time, okay? So you're sending a signal. At the same time, other computer is also sending a signal, but nothing happens, no collision happens. That's only possible if you had, instead of one link, if you had two links between these computers. This is the only way where this is possible, the full duplex communication, okay? Remember this, this is important. So in early network, only half duplex communication was possible because they were using what? Coaxial cable, which we saw. Do you remember the coaxial cable that we saw? It had just one copper cable, and then there was an insulation, and then there was a mesh of copper as well. So one was a positive, one was negative to complete the loop for the electrical signal to reach. But that just means that there is a single link. If you connect all computer using coaxial cable, there's a single link through which you can transmit a signal, a voltage level. So everyone else must listen. Only one computer can send a message. If other computers send a message at the same time, you would have collisions and no communication could happen. That's why it had half duplex communication. We solved that problem with the UTP cable, and that's why you saw inside the UTP we had 4 pairs of cable, so that one pair could be used for transmission and another pair could be used for receiving. And that's the only way that the UTP solved this problem, and we started talking in full duplex, which allowed both devices to simultaneously transmit and receive on a shared medium. Okay? The only way full duplex communication is possible because we have different wires in UTP for transmission and different wires for receiving. Otherwise, you cannot have full duplex communication. And Ethernet switches operate in full duplex mode. The switch we talk about always, when they connect using UTP or shielded twisted pair cables, the Ethernet cables, they allow, using this technology where you have UTP and a modern switch in computer, they allow full duplex communication because of this ability. And this is why today's computer can talk to each other simultaneously. You're sending something, you're also receiving something at the exact same time, and that's why we are having great communication, okay? Another terminology is that access, when you are connected to a network, whether it's a bus topology, star topology, mesh, whatever it is, there are two major types of it where you would get into a situation that how do you access that physical media when you're starting to send a message? There could be either a contention-based access or a control-based access. Again, these problems, the access method, are only appearing in half duplex communication. If you have a half duplex communication, then you have an access problem. The problem is that if you have a link between two computers, which is a single link, where you can only do half duplex communication, one of them can send, not both of them, then you need to solve a problem like how do you decide who can send and who cannot send and when to send. Okay, you need to solve this problem, and data link layer has to create a protocol for this, rules for this, who's going to talk first, how long he's going to talk, and how does it tell the other person or other computer when to stop talking, and how does the other computer know when he can start talking now, and for how long. This is a complex problem in computers in a half duplex communication. So that depends on situation, whether your network is contention-based access or control. I mean, these are two solutions. You can give it access using contention-based or control access. For example, in contention-based, all nodes operating in half duplex competing for use of the medium. In half duplex, everyone is competing to get access of this medium. Who is going to access this medium? Because only one computer can access it at a single time. Okay, so that's why there is a competition. Who is going to access it? So the solution for that, which is a whole protocol in itself that was written at a data link layer and was implemented, is called carrier sense multiple access, CSMA, with collision detection. In short, it is written like this: CSMA with a collision detection. The word itself says it carrier sense. It senses the carrier. This medium is called a carrier. It senses the carrier with multiple access because multiple people are accessing it. So first we sense the carrier to see if someone else is sending a message or not. Just listen. Okay? And then if there is any collision, try to detect it. This is used on legacy bus topology Ethernet. So bus topology was like this, right? There are multiple computers connected to a bus. Everyone needs to first sense the carrier and then try to see if there is any collision. If there is a collision, then they would back off and so on. And there's a lot of details for those protocols that we don't need to cover, but you at least need to know that what is a CSMA CD. So on this wire, if by any chance, if two computers send a message at the same time, there would be a collision. Then these computers can listen to this collision, because whenever a collision happens, the voltage level spikes, and that high level voltage would reach all the computers. So that's how all the computers know, oh, there was a collision somewhere. If there was a collision, they would detect it, and then there's another method where they would back off and everyone would randomly wait out some millisecond of time, and then they would start carrier sense again to see if nobody is sending a message, then they can send a message. Okay. A same protocol was also used in wireless LAN, which is also used today. Carrier sense multiple access with collision avoidance, with a slight changing. Instead of detection, it has a collision avoidance, and it is used in wireless LAN even today. So think of your wireless access point as a single bus, except that there are no wires. It is using a single frequency band, which is same as if you have a single wire. Okay, and then you have a computer at you have smartphones, you have computers, and you have laptops and so on, everyone connecting to the same wireless access point using the same single frequency. If you were to draw this using connection, it looks exactly like this bus topology. Okay, your wireless connectivity looks exactly like a bus topology, except that there are no wires, except you're using a wireless frequency. And because that frequency is a single frequency, everyone is sharing that frequency, you have exact same problem that you had in bus topology in your wireless local area network today in your home that you're using right now. It has that problem of the bus topology. To solve that problem, what your computers, your mobile phone and laptop has is that at the data link layer, in the sub-MAC layer, it has a protocol running which is called carrier sense multiple access with collision avoidance. This is right now running in your mobile phones, in your laptops and computer, in short, which we call CSMA-CA. This is allowing you for all these computers to connect to your same access point and use it using same frequency without having any collision. Okay? That's why if you come back to this question here, here's the reason. If you're using wireless LAN as your physical solution for at the physical layer to connect or create a network, then you have to use WLAN standard. Why? Because wireless LAN has this problem where in this case you would have to run CSMA collision avoidance, this protocol. If you were to use Ethernet cable, which we have today, if you use the wired cable to connect all these computers instead of wireless access point, then you don't need to run this protocol. That's why then at the max sub layer, you run this one, which doesn't have this. Why it doesn't have this? Because we don't even have the problem of shared access in this situation. Why we don't have this problem in this case when we use the UTP? Because it has separate copper cables for transmission and receiving. It can communicate using full duplex. If your network is able to communicate in full duplex, you don't have the problem of competing with other computers to get access to the network. Everyone can talk to each other simultaneously because for transmission and receiving, we have separate cables. In wireless LAN, we don't have separate frequencies. We have a single frequency. Everyone is sharing it. That is exactly as if you are connected using a single cable with everyone. And now you have to compete with each other. And that's why you need to run CSMA-CA. I hope that clears some of the higher level questions in your head, like why are we doing or studying all this, right? So your Wi-Fi or wireless LAN is half duplex communication. And when you're using UTP cable, that is doing a full duplex communication. Whenever you're running full duplex communication, you don't need CSMA-CD or CSMA-CA. When you're running half duplex communication, you need CSMA-CA or CSMA-CD. In wireless case, instead of CD, we have CA, collision avoidance. We have to avoid collision because we cannot do detections in wireless medium because it's shared. If there's a collision, there's no way for the devices to listen and understand if there was a collision. So the only thing they can do is add some method of collision avoidance. Because it's a half duplex and it runs this, that's why wireless local area networks are always slower in performance compared to the Ethernet cables that we use. This is why we always prefer the wired connectivity over wireless connectivity wherever we can. Okay. How does CSNA-CD work? Well, in legacy Ethernet LANs like bus topology, where we had half duplex mode, which we don't have in wired connectivity these days, we could only have one device send or receive at a time. And we used a collision detection process to govern when a device can send and what happens if multiple devices send at the same time. So this protocol was deciding this. Okay. It has a collision detection process where a device transmitting simultaneously will result in a signal collision on the shared medium. Everyone would detect that there was a collision, and then the device detects the collision and devices wait a random period of time and retransmits the data. That was the only solution. You would always have collisions, then everybody would wait some time, and then they would start their carrier sense multi-access protocol again, trying to see if somebody else is not sending, then I will quickly send my message, and so on and so on. Which is why the bandwidth utilization and optimization and the speeds were very slow, because they had to run this process all the time. There were collisions all the time. It was working, but it was not optimal. It was not fast. That's what your in legacy Ethernet LANs used to happen in bus topology, in token ring, and so on and so on. In your wireless LANs, we still have this problem, and we run CSMA-CA because wireless LAN operates in a half duplex mode where only one device send or receive at a time. Right now, even if you have 10 devices connected to your wireless access point, at a single time, only one of the device can send a frame. All other devices have to wait. Otherwise, there are collisions, and you can't even detect collisions, and that's why your wireless XN, as you increase the devices connected to your wireless access point, the performance your access point will degrade, the bandwidth will degrade, the available bandwidth to you degrades. So it uses a collision avoidance process to govern when a device can send and what happens if multiple devices send at the same time. So all of your devices are running CCNA CA, and that's how every device gets a specific amount of time in milliseconds where they can send a specific amount of data, and then they have to stop. Send and stop, because they have to give other devices an opportunity to send as well. So that's why your speed is limited when you're connecting to Wi-Fi. When a transmitting device also includes the time duration, how does it avoid collision? Every time your device sends a wireless frame, it includes a time duration in the frame needed for the transmission. So every time your device is sending a frame, there is a special field in the frame where it puts like, hey, I need to send more data for next 200 milliseconds. So everyone in the network, please don't send anything until 200 milliseconds because I am sending data. That's the thing, Asif. They don't send, your laptop and smartphone do not simultaneously send and receive data on home Wi-Fi. They are waiting. They are doing it in chunks, turn by turn. It is doing it so fast that it feels for you that it's doing it simultaneously, but in actual, it's not doing it simultaneously. Yes, they do it in very small delays, in milliseconds. So for 200 milliseconds, your computer is sending something, and it told everyone else in that frame that, hey, for 200 milliseconds, I'm sending data, nobody sends it. After 200 milliseconds, your smartphone says like, okay, now it's my turn. I will send data for 200 milliseconds. Nobody else should send it. And they keep doing turns and turns in milliseconds. So for you, it feels like everything is working simultaneously, but it's not working simultaneously in wireless LAN, okay? So all other devices on the shared medium receives the time duration information and how long medium will be unavailable. So all other devices already know that, hey, for the next 200 milliseconds, we shouldn't be sending anything because your laptop is sending something. This is a shared medium. This is shared between all of them. This is a single frequency band, which is shared between all the computers that are connected to this access point, and they have to come up with this method so that they can share this medium with each other using time durations. So that they pick times in milliseconds, and that's how they all use it. Okay. Now that you know these problems, TDD, what is TDD? It's a time sharing mechanism. Like if there is a single thing that is shared between us, any physical thing, how do we share it between two people or more than two people? You have to share it by giving them some time, right? So for first minute, I will use it. When I use it, so next minute, then you will use it. Then we'll keep turns. We'll keep taking turns. So this is a time sharing mechanism. It is the same thing it's used between on your Wi-Fi between all these devices, because a single frequency is a shared medium. Everyone must use the same frequency, and only one computer or device can use it at a time. Now that you know these things, we can talk about the frame finally. How does the frame look like when the data link layer creates and encapsulates anything that comes up from the upper layers? Okay. So a frame includes, so the data is in the middle, which comes from layer 3. So if you remember encapsulation at layer 7, you create a data, it keeps going down and keeps encrypted by layer 6, then by layer 5, and then by layer 4, and eventually by layer 3, where we had the IP header. This is where we start calling this a packet. This is where it's called a segment, a PDO, and this is where it's called a data at above layers. So data becomes segment when it's encapsulated, then it's again encapsulated by layer 3, it becomes a packet. And finally, when we encapsulate the packet, it becomes a frame at layer 2. And this is where we're talking about how does a frame look like? Well, a frame has a data which came from layer 3, and we encapsulate it in a header. We add a header and we add a trailer to that data. and then we say that this is a whole frame. So we cover the data coming from layer 3 with a header and trailer, and we call it a frame. Okay. So what do we add in the frame? Well, there are multiple fields in the header and trailer which vary according to the data link layer protocol. Remember, we said depending on what physical link you are using, what physical standard you are using at the physical layer, the data link layer protocol changes. And because the data link layer protocol changes, the frame header and trailer also changes based on which protocol you are using. For example, if you're using a Wi-Fi, the frame will look very different because Wi-Fi has its own problem which this frame needs to solve. One of the big problems we saw was the CSNA CA needs to be run. Time sharing needs to be done between all devices in Wi-Fi case because it's a half duplex communication. And that's why when you're using Wi-Fi, you're using a WLAN protocol where CSMA CA needs to run, and the header in this case would need to include a specific field in which you would say, hey, I need this Wi-Fi frequency to be used for 200 millisecond. Everyone must know this. This information is not needed if you are not using WLAN, if you are using wired connection. So that's why now you see if you are changing physical connection at the data link layer, protocols would change and the frame would look very different for different physical connectivity. Okay. So this is a normal frame that looks like. This is not specifically for any specific protocol. This is like a generic for Ethernet frame. If you were connecting using cables, this is how the frame would look like. So you have a data from layer 3, it gets encapsulated in a frame, you add a header and a trailer, and it has a frame start bits which identifies the beginning and the end of the frame. So you have a frame start and a frame stop. So because this is the whole thing you would be sending to the other computers, so it must have a specific pattern of bits in a frame start and a specific pattern of a frame stop at the end, so that the receiving computer can easily tell where the header starts, where the frame starts, and where it ends. So it knows exactly, oh, this is the whole frame that I just got received. Okay. So at layer 2, we add a frame start and a frame stop. We add addressing. This is important. If you don't add addressing, you don't know who is sending frame to who. Okay. So in the addressing, you must have a source address. You must have a destination address. How does these addresses look like? Depending on what protocol you're running, these addresses could be anything. But in specific, in Ethernet frame, which is most commonly used, these addresses are source MAC address and destination MAC addresses. I'm talking about only wired Ethernet frame. If you're using wireless LAN, the frame addressing for that wireless LAN would look very different than the normal frame, because it has more problems to solve. Okay. The type of encapsulation, it identifies the encapsulated layer 3. The type shows like what kind of data inside a packet is. This is a layer 3 IPv4 address, IPv6 address, so it gives that information. Then we have a control information where we identify the control services, different control services, and error detection bits if we have errors that could be corrected or at least detected. How would addressing know the destination MAC address? That is not question for today's module. We will be covering that in a different module, okay? For now, you just need to know the layer 2 addresses, how do they work, okay? So layer 2 addresses are referred to as the physical addresses contained in the frame header, just like we saw, used only. The source IP address and destination IP addresses are not part of layer 2. We are only talking about layer 2 header. So inside layer 2 header, we are only talking about physical addresses. The IP addresses are inside layer 3. We are not talking about it. Today, we are just talking about this data link frame, which is a layer 2 frame. Okay. So they're used only on local delivery of a frame on the link updates by each device that forwards the frame. Okay. So your computer has a network interface card. It has to send it first to R1, then R1 has to send a, don't know why this keeps happening. Let me clear this. So your computer, if it wants to send data from here to here, it must first solve this problem, how to send it to R1. And R1 has to solve this problem, how to send it to R2. And then R2 would send it to final destination. Okay? So every time we studied in the beginning that the responsibility of data link layer is that it is responsible for sending a frame from one network interface card to other network interface card in the same network. So your computer has a network interface card. It has to reach the network interface card of the R1 port. That is the only responsibility of the data link layer. It does not have the responsibility to send it from here to here. That responsibility does not belong to layer 2 frame. Okay, this is not the job of data link layer. The data link layer job is only up to here, from one NIC to another NIC. Then again, from one NIC to another NIC. Then again, from one NIC to another NIC. So after each hop, data link layer is only providing solution how to get to the next NIC. That's it. It doesn't care about whether your traffic is reaching all the way to this destination. It doesn't even know about it. It doesn't even know that that's what we are doing. It just knows that I have to send this frame from this network interface card to this network interface card. That's it. My job is done. Okay. So in order to do that, whenever you create a packet here, your layer 3 information gets encapsulated in layer 2. You create a frame, and obviously this one is saying like you have layer 3 packet encapsulated in layer 2 frame, and this layer 2 frame has this inside it, a destination NIC MAC address and source NIC MAC address. The layer 3 has this information, source IP and destination IP, but we have to hide it. We are not looking at it. We just know it's inside the frame in the data field, but we are not reading it. We don't know what's inside it, and we don't even care about it, what's inside it. Okay, we only care about this because the data link layer job is just to get from this NIC up to this, and your job is done. So in the source MAC address, it just puts its own MAC address. Let's say it's a is a MAC address, so it will put A. And then it would, in the destination MAC address, it will only put the MAC address of R1's this interface, which could be, let's say in this case, it's B. So put B in the network. So if you look at the addresses in the frame, it just says that, hey, I am computer A, and I'm sending this frame to R1 whose MAC address is B. And that's it. It doesn't care about anything else, nothing. And this information, this frame doesn't have any information about this computer at all because it doesn't care. Because the responsibility of a data link layer is just to get this frame from here to here to a next hop, from one NIC to another NIC, nothing else. Please, I'm saying this again and again. Put this in your head. The data link layer's job or responsibility is to get the frame from one network interface card directly to another network interface card that is directly connected to it in the same network. And that's it. Okay? It doesn't care about anything else. So let me just go through it again. Let me just see if it's explained. Oh, it's not explained. So it's just one slide. So let me explain it again. Okay? Listen carefully again. The data link layer job here is that when I type, like let's say when I type here, like ping A.A.8, let's assume this is the A.A.8. This is the Google server. This is the IPv4 address of A.A.8. So what my computer is going to do, I'm not hitting enter. Let me just show you IP config. So my computer has an IPv4 address of this 192.168.118.80. So let me put that. So my computer will generate a layer 3 packet in which it would say that what is the 192.168.18.80. That would be the source IP address that my computer puts in the packet. Then the destination IP would be if because I am providing the destination IP is 8.8. So my computer, as soon as it hit enter, my computer will create a packet at layer 3 in which destination would be 8.8.8, and that computer is somewhere around the world here, and I'm connected to my access point, and then the ISP is connected to other routers around the world, eventually reaching connectivity up to that Google server, right? Now, if I look at the, does it show me a MAC address here somewhere? It's not. So if I do ipconfig /all, it will show me my Wi-Fi address is here. Where is the MAC address? Here is the physical address. This is the MAC address. So in short, this is a 48-bit MAC address written in hexadecimal. In short, I will just type 28. So this is my address. So my computer, when creating a frame in source NIC, it will just say 28. This is my MAC address. Now here's the interesting question. What would be the destination MAC address? It cannot put the MAC address of this computer. That's impossible. There is no way to find out for me what would be the MAC address of this computer. My computer cannot find it as well. My computer, because this is destination MAC address at a data link layer, remember, the responsibility of a data link layer is only to get this frame from here to here. That's it. My first hop, which would be the default gateway, which is, in my case, at my home, is my default router, my access point. So it needs to find the MAC address of this R1, okay? Because that's its job. The frame's job is up to here. It doesn't care about if your packet reaches here or not. It doesn't care about that. It just needs to get you from this point to this point, and that's it. So what my computer would do is, using ARP, it can find out like who is the default gateway. Let's say my default gateway is 192.168.18.1. We will go through this process in details later on. I'm just giving you a high level steps. So my computer will try to find 192.168.18.1, right? Yeah, 18.1, and it tries to find the MAC address here. So here is the MAC address of my access point. Okay, so in here, let me show, in short, I would say 6C. So it will put 6C here, which is the MAC address of this R1. And then it will send this on this wire. It will get received here. This whole thing will be received by R1. What R1 would do, it would remove all this information, expose this, reads the destination IP 8.8, and makes a decision, okay, to reach 8.8, I have to send it in this direction to R2. Okay, that's just a decision made. But how to send it? Again, it have to create a new frame here now. So it will create a new frame here, and it will see, like, because the frame's responsibility is just to send it from one NIC to another one. It just needs to send it up to here. That's it. That's the responsibility of frame. So it will create a source NIC. In this case, let's say its MAC address would be B. So it will say source MAC address B, and it will try to find the MAC address of this R2. Let's say it's C, and it will create this new frame, which is totally different from what we sent from here. Remember? Because when we send it from here, the source MAC was 28, the destination was 6C. This was the source, and this is where it was sending it. Then it removed that frame, and now it created a completely new frame where the source is B and destination is C. And then it will send it on this wire, and this computer will receive it. This router will receive it. This router will again remove this whole frame, expose the layer 3 data, look at the destination IP, and now it knows, oh, here is the final destination where it's sent to, but in order to send it to, I need to create a new frame so that I can send it from this NIC to this NIC, and then again, it will create a new frame where, let's say, its MAC is D and this MAC is E. So it will say source is D and MAC address is E. and it will create this new frame, completely new frame. It's totally different from this one. It is totally different from a frame that was sent over here. It's a completely new frame with new source and MAC addresses, and then send it here, and this is how eventually it will be received on this computer. Okay, so the high level idea that you need to take from here, and this is something we'll be doing in Packet Tracer again, so no worries if you don't understand it. I'm only giving you a very high level idea that every time you send something and it has to go through multiple hops to reach it, the layer 2 frame is changing at each hop. At each hop, a new frame is being created. A new frame is being created with completely new source and destination MAC addresses. So every time, so if you now read this definition that we read at the beginning, it will make sense. Where is it? Let's see. Where was the definition? Yeah, so look at this one. At each hop along the path, a router performs 4 basic layer 2 functions. It accepts a frame from the network medium. It de-encapsulates, meaning it removes the frame headers and trailers. So it de-encapsulates the frame to expose the encapsulated packet, meaning it reads the layer 3 information in which it reads the destination IP. Then it re-encapsulates, meaning it creates a new frame. It re-encapsulates the packet into a new frame. In this new frame, it uses completely new source MAC address and destination MAC address. And after that, it forwards. So every router is doing this same thing again and again. Now let's look at this. If I do this, my computer generated a frame with the source MAC address of my computer and then sent it to the destination MAC address of my access point. And just for this one packet. And then my access point de-encapsulated that frame, exposing it looked at the destination IP address and created a new frame to send it to my ISP router with source MAC address of my access point and destination MAC address of my ISP router. Then my ISP router de-encapsulates the frame, reads the destination IP, then re-encapsulates it with completely new source MAC address, and it keeps doing that again and again until it reaches to the Google server. And then Google server responds back, doing again and again. Every router in the hop does it again and again. If I want to find out how many routers did this process of de-encapsulation, reading the destination IP address, and re-encapsulated with new source and MAC addresses, I can find it out with trace-RT. How many? Just to give you an idea of how internet works. So it says that this route is being traced up to my Google DNS servers into 30 hops. So it should complete before 30 hops. So let's see how many routers in between my laptop and Google server are there. So this is the first router, which has this IP address. This is my access point. And then my access point is connected to my ISP router, who has this host name and this IP. And then my ISP router is connected to some other city through maybe fibers. Then another router, it keeps going. It keeps going. Maybe this is where I think it went out of my country through undersea cables to a different country and so on. And eventually on the 10th hop, it reached the DNS Google server. So between my laptop, I'm sitting in Pakistan, and the Google server, I don't know exactly where it is, but probably it's in US, depending, because they have CDN and so forth. It not necessarily in US, but at least it's not in Pakistan, right? So there are 10 routers, or at least 9 routers, because this 10th is the Google server itself. So there are 8 routers, because the number 1, this is I'm myself. Sorry, this is not myself. This is my access point, which is acting like a router. So this is correct. So I have 9 routers between my laptop and the DNS, Google's DNS server. Each router is doing the same thing. It is de-encapsulating the frame, reading layer 3 information, destination IP, and then re-encapsulates with new source and destination MAC address at each hop. It keeps doing that. So at each hop, the data link layer is doing just one job at each hop. It is just trying to send from one network interface card to another, from one to another, from one to another. It keeps doing that again and again. Eventually it reaches here, and then in the reverse process is also the same. Okay. So if you understood this today, then you are good to go. Now we can okay, I think we missed this slide. So the logical topology in physical diagram, the data link protocols. Okay, so we have different protocols that goes and solve different problems. When we are using wired network with UTP and STP cables, we are using Ethernet frames, Ethernet technology, Ethernet protocols. So at the data link layer, we say that at data link layer, we are using Ethernet protocol. That means I know, okay, we are using wired network, and inside the frame looks like this. It has source and destination MACs. If I say I'm using Wi-Fi, then I know at the data link layer, we are using 802.11 wireless protocol, which, because wireless has this problem of shared medium, we need to run CSMA. Whenever I say wireless, you should know that naturally it would be running CSMA CA. It will be running CSMA CA to avoid collision. It is half duplex, and it has more problems to solve, and the frame would look very different in wireless medium. It wouldn't look anything like Ethernet because it needs more fields to solve more problems. If you have point-to-point network, in that case, we can use point-to-point protocols, because point-to-point network is simpler than Ethernet and wireless because it doesn't have any such problems. It doesn't have addressing problems. There are just two devices connected to a cable. There's no shared medium. It's not half duplex. So it's a simpler protocol. Similarly, we have other protocols at data link layer as well, called HDLC, created by Cisco. We have frame relay. So in different situation, in different physical connectivity, how we physically connect and what standard we use, at data link layer, we would have a different protocol to solve the problem that are specific to that physical medium. Okay. And that's it for it. You can go to your module 6 in a Netacad. There are small quizzes and terminologies that you should go through to reinforce your learning, whatever you learned here, so that it sticks in your head. And if you don't understand anything, I'm always there. In the group, you can throw questions. So far, I don't see any questions in the group. I hope to see some questions so that we can reinforce the learning that we are doing from these classes, okay? So now you learn some high level, now we are getting into some high level discussions, terminologies. So from next module, next week, we will get into a bit more details of switching, and we'll start doing practice again on the lab to exactly see the process that we just discussed, okay? Yeah, no problem. Thank you, everyone. So I will see you in the next class. Meanwhile, I will be putting recordings and the lab recordings as well for some of the labs that we do in a packet tracer. So far, nothing so technical in packet tracer, but there are some labs that I'll be sharing with you, which goes through everything that we have covered so far. So if you just watch those and try to do those in packet tracer as well, just to reinforce what we're learning so that you memorize these terminologies. Because from next class, we are getting into a bit technical details of how switching actually works, okay? So if you don't cover what we have covered so far here, if you don't go to Netacad, if you don't watch the labs, then I think you would start having problems from the next session, because things are getting a bit technical now, okay? See you in the next class.